Hi all, we have one more equilibrium constant to discuss. We've seen Kc, Kp, Ka, Kb, Kw. Now we're going to look at Ksp, solubility product constant. Actually, many salts are not very soluble in water. They have limited solubility. So in part A, let's say that many ionic compounds, or in other words, salts, have limited solubility. We are assuming water, limited solubility in water. For instance, barium sulfate man, something's in my throat, is an X-ray contrast agent. That's pretty insoluble. It can eventually be excreted, but since it's insoluble, or fairly insoluble, it stays intact, or it stays undissolved, and shows up in the digestive tract. To show any gut ailments. I did not mean to write so much about barium sulfate. Another example is hydroxyapatite. Ca5. It's a big ionic compound. But you might have heard of hydroxyapatite, because that's tooth enamel. You don't want your tooth enamel to be soluble in water, but if you have too much acid in your saliva, then it will dissolve. Insoluble, usually. But soluble in high acidic soda, coffee environments. Therefore, understanding how these different ionic compounds dissolve and giving them some quantifiable number to show how much they dissolve is very important. And that is going to be Ksp. So now let's show you what Ksp literally is. Ksp is called the solubility product constant. And if you have a salt, let's just call it Mx. Yeah, we'll call it Mx. So M is a metal, X is some anion. It doesn't have to be a halogen, and it's solid. And you dissolve it in water, and there's an equilibrium established. And I'll put water on top. And then the equilibrium is you have a metal. In this case, it's positive, aqueous, plus some anion. In this case, it's minus. We're going to assume it's minus. This could actually be m2 plus and x2 minus and just reduces to 1-to-1 ratio, but we'll assume plus 1 and minus 1. Well, you know your equilibrium constant when you're looking at concentrations is equal to these two multiplied. But what's interesting here is that the reactant does not show up in the equilibrium expression because it's solid. You know that you don't include solids and liquids in equilibrium expressions. And this has a special name, and it is called the KSP. So when you have an equilibrium constant that is focused on the solubility of a salt, you typically call that KSP. All right, let's practice. Let's say we have silver chloride. Write the KSP expression for AgCl. AgCl. You want to do this on your own? I'll give you, go ahead and pause it, and then unpause it when you're done. Okay. KSP. Honestly, what you really should be doing is always start with a chemical equation when you're doing KSP expressions. You don't have to write water, Ag plus, but it is helpful to write the states. Cl minus. Okay. So when you break up these salts, it is your responsibility to know what charge these salts are, or these ions are. This is from General Chemistry 1 when you were doing stuff like net ionic equations. You were breaking up compounds into their ionic parts. Concentration of Ag plus times the concentration of Cl minus. Not too bad. What about copper hydroxide? CuOH2S. Could we write an equilibrium expression for that? A KSP expression for that? Well, let me just work off of this compound. How about you fill in the products and write the KSP expression? Pause the video. Okay. We have copper. It is plus. No. It's actually 2 plus. So this is why it's important to write the chemical equation. Plus, remember that 2 represents two molecules of OH minus per 1 molecule of CuOH2. It's a coefficient, right? 2OH minus aqueous. Does that change how we consider the KSP? Yep. You have the concentration of Cu2 plus, okay, and times the concentration of OH minus, the hydroxide. But now that you have a 2, you do have to square this term. Okay. Are the types of problems that you might encounter are they obvious? It seems like the problem might be we give you the KSP and you have to figure out the concentrations of the ions. Or it could be you're given certain concentration of the ions and you have to decide, is the reaction going to go forward or reverse? Or finally, we may give you some initial conditions and you have to calculate for the KSP. Now let me give you a challenging one where we're going to have several subscripts, maybe coefficients, and also we're not going to use the actual elements. We're going to give you a generalized salt. M2 M2X3 solid. Could you write the products and the KSP expression for this one? Okay. Well, we definitely have, we're going to pretend that this all dissociates or ionizes, same thing. And we have two metal cations. Those two metal cations have a 3 plus charge. And we'll double check. But that 3 is because we need 3 of these X's for every 2 of these M's. Let's guess a 3 plus charge for now. And again, get in the habit of writing the phases. For the X, we have 3X, and that is, we're going to give it a 2 minus charge. Okay, pretend that we had this. Okay, this is your check. If you had M3 plus and X2 minus, how would those combine to make an ionic compound? Remember the trick drop and swap? You drop the charge and you swap them. So now we have M and X. That 3 goes here, that 2 goes here. And then you can double check, because if you have 2 M's, you have a net plus 6 charge, and if you have 3 X's, you have a net minus 6 charge, and they cancel out, they balance, because we have a neutral salt. Alright, so that's where we're getting the charges, and then obviously the coefficients are from the fact that you have 2 atoms of M and 3 atoms of X per 1 molecule of M2X3. KSP. Were you able to write your KSP expression? Okay, we have concentration of M, 3 plus. You do have to put the charge, okay? It's not concentration of just the M, it's a concentration of the ion, that's squared, times the concentration of X2 minus ion, and that is cubed. That is cubed. Okay? And that's it for now. It's very important that you be able to draw or write the KSP expression properly. Before we conclude this video, let me ask you actually, if I have, this is a little tricky because of the stoichiometry. If I have some amount of M2X3 and I let it throw it into water and I let a lot of it dissolve, or I let it dissolve, but I still have some solid left on the bottom of the beaker, well, that means I reached saturation. So at saturation, if I have 0.005 molar of M3 plus, what is the concentration of X2 minus? They're not equal, right? Because look at the coefficients. So in this case, what would we do? We have to do maybe a mole bridge. 0.005 molar of M3 plus times, or maybe you can do this in your head. I'm sure some of you can do this in your head, but I kind of worry about my ratios. For every 3 moles of X2 minus, I have 2 moles of M3 plus. Okay, the moles cancel out. You see what cancels out? That cancels out, that cancels out, and these two. So I'm going to get a molarity of X. 0.005 times 3 divided by 2. Okay, is it more or less? 0.0075 molar. It is more, right? It is 1/3, no, it's 50% more. Do you see why? Because look at the ratios. Okay, so this is a tricky part. When you plug in the numbers here, those two concentrations are not equal. Remember that for the next video. These two concentrations are not equal because their coefficients are not equal. And then when you figure out the KSP, or not the KSP, but if you try to figure out, in this case, Q, because we don't know if these concentrations are at equilibrium, you could figure out a QSP, right? And you have 0.005, but don't forget it's squared. There's a lot of things to remember when you do these types of problems. And we'll formally do several problems like this with real compounds in the next couple of videos. And this is cubed. So now you can figure out the QSP. I didn't give you the KSP for this salt, but then you can compare Q to K. And then you could figure out, right? Does it shift left? Does it shift right? Or if Q equals K, it's already at equilibrium. It's already at equilibrium. But again, just keep in mind that we're going to have to be able to do something like this because those two concentrations are not equal anymore.